on to our final speaker, Ron Macnaughton, and they'll tell us about from Messiers to spiral arms. And
years ago at a star party, I had chatted with the cook for a while, and when he finished his duties, I had my telescope set up, and he came over and we were chatting, and I asked him if he wanted to look at something, so I pointed my 4-inch telescope, let's see, at that. And we all know what that is. Most of the time I find when people look through my scope, they look at it a little bit, and there's usually a comment about, wow, that's beautiful. And there are other people in line, so they don't stay too long. He looked for a good solid 2 or 3 minutes and said nothing. And then I said, after that, you know what do you see? And this guy might have been just a cook, whatever that means, but he had staggeringly, I'm trying to get the laser thing, he had staggeringly accurate description. He said, and this is a 4-inch telescope, remember? He said, well, it looks like it's flat, but it's tilted to one side. It's brighter in the center, and it gets less and less bright as you go outside. And he talked about something that there were dark circles in it. I mean, what a description. And he wasn't even an astronomer. He was just hired as a cook. And then I said, what do you think it would look like for somebody maybe halfway out inside here? What would the sky look like? And he said, I really don't know. And then I said, look up. And he went, wow. Because it's exactly our situation inside the Milky Way. And we have these, oops, wrong way. Can I go back? Yes. Sorry. We have this pattern here of, and of course, this is the summer Milky Way. This is Altair, etc. So that's it. We can actually figure out a lot of the patterns of our galaxy by looking at the patterns of the Milky Way and specifically the Messier objects. So, too far. All right. So I'm going to show you a number of maps showing you all sky. So this is zero right ascension, which means that the sun is in front of these stars on the spring equinox. And in the spring, we have a nice view of Leo and that sort of constellation, and of course the Virgo cluster. In the summer, the sun goes further north, and it's in front of the stars of Gemini, my zodiac constellations. You know everything about me from that. And of course, the Great Orion. And what can we see at night in the summer but Sagittarius and Ophiuchus and etc. Then you go one more season later, the fall equinox, it's here. And in the fall equinox, you have the great view of Andromeda and M31. This was August or September, that star party. And of course, in the winter equinox, these are all next to the sun, and we have a great view of Orion and the wonderful gems there. This line that I put on, and is not that accurate, is the rough brightest spot of the Milky Way. So the Milky Way goes up through Sagittarius, Aquila, up Cassiopeia, down through my zodiac constellation, and down into the south. So what do you think the concentration, the pattern, the next picture shows the Messiers. Any prediction on the pattern of the Messiers? This is all the Messiers. I found a program. By the way, I made this talk up 15 years ago, and I couldn't find the program. But these are all the Messiers. Now, Chris and Charlene, is the reason there are no Messiers down here because there's nothing in the southern sky worth looking at?
Mr. Messier.
Obviously, he lived in Paris and couldn't see the south. But there are more patterns than that. You notice that there's quite a bunch here around Sagittarius, but there's also a bunch around Orion. And that tells us something about the strategy, the pattern of the galaxy. Now, there's a bunch here, and this is the Virgo galaxy cluster, and I'm not going to talk anything about external galaxies because they don't tell us much directly about the Milky Way. I'm going to go now type of object. So I'm starting with globulars. And globulars are some of the oldest things in the universe. They have, let me go back. wrong button. This one. They have maybe 1 million stars. There's very little dust. They don't flatten because the dust, when dust goes down and dust goes up, it cancels out. But this has no dust. They're very old, and they're all over the place. So, predictions. Where do we have most of our globulars, or are they random? Comments?
They're near the core of our galaxy.
So most of the globulars are Sagittarius region. There are a few that are on the other side of the galaxy, but most are near the core. And Harlow Shapley, I think that's his name, he measured the distance of globulars in the, 1910, something like that. They looked at variable stars, and from the period of variable stars, they can work out the intrinsic brightness of those particular stars. And he got distances to to the globular clusters, and he found they cluster in a spot about here that turns out to be something like 27,000 light years away. So that data showed that we're not in the center of the galaxy. The center of the galaxy is over here, and it's also towards Sagittarius. Why isn't it moving on? It turns out radio telescopes found a source of radio waves, Sagittarius A star, for some reason it's called that, that's there. And when they use infrared telescopes, this was taken in infrared, which penetrates through all the dust that's near the center of our galaxy. And these stars go around this spot, and then it zooms in, and there's one star, S2, that goes particularly close to it. And this is a summary. Didn't I say I gave this talk a long time ago? 2002 is the latest data. I'm sure they've got another orbit since then. And I actually gave this to my grade 12 students because if there's a moon found around an asteroid, they can take the average distance of the moon away from the asteroid and the period of the time it takes to go around, and they can get a very accurate measurement of the mass. And when you do that here, as my students were able to do with a little bit of help from me, they find that there's something in the center of the galaxy that's about 4 million solar masses. And of course, that's the black hole that's the center of the galaxy. I read somewhere, but I haven't confirmed it, that there are 2 black holes in the center of M31. So, but that was a while ago. All right. We also can see something else by just looking at this, and that is the Milky Way is wider in the Sagittarius region, and it gets narrower as it goes further up. So just from our eyes, plus a little bit of measurement, we get a model of the galaxy that it's wider in the center. We're something like halfway out, although I'll get to that in a sec. And you have a bulge here, and it's mostly flat, just like M31. This was the size of the galaxy then, but it turns out the latest value is closer to 180,000 rather than 100,000 light years. But I haven't, other than the one graph where I added the Milky Way, I haven't changed any of the graphics here. Okay, now I'm going to look at diffuse nebula, such as, of course, this is the Orion Nebula. And these are star-forming regions, so it contains all sorts of dust that has collected in one area. Gravity's pulling it together. This is a not very good photo of the triangulum, of the trapezium in the Orion Nebula. And this is a very good Hubble photo showing some of these, and these are stars that are forming right now, and it's kind of amazing to see that. Okay, so I have to now use this. All right, what's the distribution of the diffuse nebulae going to be around the galaxy, around the Milky Way? Any thoughts? Right on the Milky Way? Well, we'll see. I guess I have to press this button. Now, there are a few interesting things about it. There's a clump of them around Sagittarius. There's a clump of them around Cygnus. And there's a bigger clump around Orion. And there's a clump down here. And I've never seen those things, so I can't comment much. But it's not just that these are on the Milky Way, but they're also concentrated in certain areas of the Milky Way. And something I find amazing is the constellation Aquila, right in the middle of the core of the Milky Way, doesn't have a single Messier in it. And it only has a few objects. And I'm going to get to the reason for it in a bit. Nope, I have to use this. Now I'm going to look at open clusters. Now, basically, if we waited a few 100 million years from the picture of the Orion Nebula, it would look like this. Forming stars, slowly drift apart, and this is Subaru or the Pleiades. The closest cluster I've heard is, believe it or not, the Big Dipper. Because according to the data I got then, these stars, not counting Alkaid and Dubhe, but all these are almost the same distance apart away, and they're all moving, although that figure was different when I researched it, but I didn't change it. And that's probably an open cluster that formed a long time ago. So, what's our pattern going to be for open clusters? Thoughts? Remember, they're places that used to be star-forming regions? They are mostly even, but, they are on the Milky Way, although they seem to vary from the Milky Way more in the Orion area. And interestingly, there are more of them outside than there are, like this is the galaxy towards the center of the galaxy, and this is away from the galaxy. Last type of object I'm going to talk about is planetary nebula, which is sun-like stars at the end of life, and supernova remnants. I'm leaving the galaxies that were part of Messiers' list for later. They both produce dust that spreads into space, that gets into new stars and new solar systems that turn to make our planet something other than something made of hydrogen and helium and a little bit of lithium. So this process is important for stellar evolution. Predictions on the planetary nebulas.
Random.
Wow.
Table.
Smart people. They are much less clustered on the Milky Way than the other types of objects, though the dumbbell is bang on the middle. But they're more random, and I figure that might be because the planetaries can't be very far away. They don't last long, and they're not very intrinsically bright, so they have to be relatively close, but I didn't get to research it. Any predictions for supernovas?
In our galaxy or in the whole sky?
Oh, in our galaxy, yes. Just Milky Way
So
supernovas.
It's been what?
Pardon me?
In the last 500 years has been one?
I have one that goes to,
Remnants themselves?
I think it's 160 AD, something like that. I can't remember the number. Any predictions?
Are you talking about the remnants that we see also? Or?
Oh yes, that were supernovas, and many of these were observed by Chinese astronomers, and there was a really major supernova, and there isn't a word written in Europe about it. And this was really bright. That just says something about the mindset of Europe.
Yeah, pretty much on the line.
They're pretty much right on the line of the Milky Way, with the exception of a couple here. Is that 185? Now, looking up this, the value was 1680, and I put a question mark. I didn't change the number, but if someone's looking for details, that is incorrect. So these seem to be right on the Milky Way, but maybe they're relatively recent stars that were, like Jimi Hendrix, live a rapid life, shall we say. And so they would form right on the Milky Way, and they haven't had time to move away from it. Who knows? So, we look at distant galaxies, and of course we see spiral arms. So, what causes the spiral arms? Okay, there's spiral arms. I'll explain later how spiral arms get started, at least one theory. I do want to say one thing about spiral arms, though, is in this one, we're here, and there's a spiral arm outside of us that has the Orion Nebula and the many objects for Orion. Remember there was quite a bunch up of objects around Orion? And this one has a whole bunch of objects pointing towards us, towards the center of the Milky Way. But you notice that I said Aquila didn't have any Messiers in it? And Aquila is in this distance between the spiral arms, and maybe that's why, or maybe it's just a lot of dust. I don't know. But we can see evidence of the spiral arms. And also looking opposite Aquila, out here, there were relatively few objects here as well. So the fact that even on the Milky Way, it's not evenly spaced is reflected in our pattern. So we're here. We've got the Orion arm outside us with M42 and a whole bunch of other things. And inside, towards the center of the galaxy, we've got Trifid and Lagoon and a whole bunch of summertime objects we see here. Now they feel it's more a barred spiral than is shown here, but this goes back 15 years. This is the explanation for spiral arms. The theory is that the stars are moving a little faster than the spiral arms. And just like when you're driving along, sometimes you get stuck in a slight slowdown and it takes a while to get through, and then you can go back to your normal speed, depending on the highway, of course. And actually, there's a name, they're called kinematic waves, and I've actually seen papers by traffic engineers about them. So the individual cars move through the traffic jam, and in the density wave theory, you've got incoming clouds and stars. They get squeezed when they hit the spiral arm. Stars form. Some of them don't last long. Some of them go through, and that's the theory for there. But what about speed? Anybody notice something about the speed of the different planets? The third rock from the sun goes about 30 kilometers a second. They're 9 dots.
The further out the planet is, the slower it's
The further out, it's slower, but there's also 9 dots. Because I made it a while ago. Now, you would think in a galaxy that most of the mass is centered here, and as you go further out, the stars would slow down. And they can measure the speed of the stars because if the sun is here, this is a picture of another galaxy. Probably a lot of you know the name. I don't know, is it 101? Anyway, using Doppler shift, you can measure the speed of the stars here and the speed of the stars here towards us, and they can figure out the relative speed. And they find that unexpectedly, the speed does not follow the Kepler orbit that our planets do, but it sort of wobbles. And of course, that's evidence for dark matter. And here's our the barred spiral to show the later theory. Okay, here's the Messiers. Notice that in the spring equinox, the sun is somewhere around here, and you can see most of the Messiers in a marathon. And that's why this is the only time you can run a Messier marathon. I guess you could try it in the fall equinox, but I think the Virgo cluster would be brutal. I want to talk about a galaxy up here. Yeah, right there. That's M51, or the Whirlpool Galaxy. Now, this is the Milky Way. So this is looking straight below the Milky Way, and the Whirlpool Galaxy is looking straight up. Now, what I'm going to do is, this is a photo of M51. There's a second galaxy, and it was Hubble published this, and they allowed you to zoom in. So I'm going to zoom into this area because the sun's position is analogous to somewhere here, between two spiral arms. So I zoom in more. See those two? So I zoom in more, and I zoom in more, and one of these stars could be sun-sized. I don't know for sure. And if there was somebody living there, looking up, they would see a galaxy in the sky that is also face-on, we call the Milky Way. And who knows if they wonder if their galaxy has the spiral pattern that this Milky Way does. And also maybe they wondered if there's somebody at the other galaxy looking at them. Thank you very much.